All right, here we are again in the very last week of the course, which will come as a bit of a relief to some of you. So just for this last week, let's get into it. On the agenda today, as always, a recap on what we have learned. So I'll talk about odds and log odds, something we introduced last week. And then we'll get into, the issue with using linear regression models if your dependent variable is a categorical dependent variable where some event either happened or it didn't happen, because this is going to cause us some problems. And then once we understand these problems, we'll take a look at a solution to those problems, and that solution is logistic regression analysis. So I'll give you a bit of an introduction to how that works, logistic regression analysis, and we'll take a look at how to interpret the effects of our x variables on our y variable in a logistic regression model. So what did we learn already? We discussed some basic mathematical transformations the last time. We talked about exponentials, logarithms, and more specifically natural logarithms. So just to remind ourselves, what is exponentiation, what is taking exponentials, it's the idea that we take some base number b and raise that to some power n, and that will give us some value x. So we start out with a base number, then we pick an exponent n, and then that tells us by how often we have to multiply the base number with itself, and that will give us some value x. And we saw that logarithms are basically just taking the reverse of that. Yeah, so the idea that we can pick some base number and then think about, okay, given that we have this base number, to what exponent n would we need to raise this base number to get a value x? Yeah, so that was the idea of a logarithm. So it's basically just doing the reverse or then taking an exponent. So these are two mathematical transformations that we saw can be interesting as transformations of our x variables in linear regression models. And specifically, we took a look at one specific type of natural logarithm, the so-called natural logarithm, where the base number is not something you pick freely, but it's always the same number. It's the number that's indicated with this letter E, which stands for Euler's number, which is round about 2.718 rounded. And so that's the idea, that we have a logarithm where always the base number is this Euler's number, this 2.718. And we already saw that there are different ways to write that in a mathematical formula. We could either say, well, a log e of x is n, or ln of x is n. It all means the same thing. It's all referring to taking the natural logarithm of a number. Yeah, so these are just different conventions on how to write that down in a formula. So we already saw that the natural logarithm of a value for a variable x has a nonlinear but monotonic relationship with the original untransformed variable value of that variable x. So you can think of that as kind of like the letter R indicating the shape of the curve. So the idea is that a natural logarithm always goes up if the original variable also goes up on its value. So it's a monotonic relationship. If x goes up, then the natural logarithm of x also goes up, but it does so at a decreasing rate. So the further we increase x, the smaller the increases on the natural logarithm of x become. So we get this R-shaped relationship between x and natural logarithm of x. We also discussed odds, where we said, well, the odds are defined as p divided by 1 minus p. In other words, the probability that something happens divided by 1 minus the probability that something happens. In other words, how likely is it that something happens compared to how unlikely it is that something happens. So those are the odds, and we already saw that we can transform these odds using the natural logarithm. So we can apply a natural logarithmic transformation to the value that we get for the odds. So if the odds are our original variable x, then we can do a natural logarithm of that variable, of those odds, and then we will get something which is often referred to as the log odds, which is the same thing as saying we are taking the natural logarithm of the odds, which sometimes you will see is then being written as ln odds, means exactly the same thing. It's just that there are different conventions on how to write the natural logarithm. And sometimes you will also see that instead of using the odds as a word, people will use the formula for the odds, so p divided by 1 minus p, and of course then you can get different combinations of how to use the natural logarithm in the notation and how to use the odds in the notation. So all of these different ways of writing it all mean exactly the same thing. So I'm just showing you this because you will encounter all of these different notations in the wild, and so it's going to be useful to you that you realize that all of this just means exactly the same thing. All of these are just different ways of writing the formula for the log odds. Yeah, and what we saw is that if we look at what is the relationship between the probability and the log odds, so the natural logarithm of the odds, that we get an S-shaped relationship. So if we put so if we look at how does the probability change if the log odds increase, then we see that the probability increases at first slowly, then increasingly quickly, and then the rate of increase in probability decreases again. So the overall relationship between log odds and probabilities, if you put probabilities on the y-axis, has a shape like the letter S. Yeah, so it is a monotonic relationship. So if the log odds go up, then the probability also goes up. But it's definitely not a linear relationship. It is a relationship where we see that the rate of change in the probabilities at first increases and then decreases again. So we get this S-shaped relationship. So that's a bunch of different mathematical transformations and relationship between different transformations and the statistic, the odds, that we already saw so far. And today it will become clear why we reflected on these transformations and this idea of taking the natural logarithm of the odds, because today we're going to introduce a logistic regression analysis, and then we'll see that it is basically entirely based on relying on these different types of transformations. So let's start out with, why is there a problem in the first place with just using linear regression analysis the way we have already learned during this course if our dependent variable is a categorical dependent variable? So let's take a step back and first think about, what is it that we're actually doing? When we say we have some kind of categorical dependent variable, and let's assume, as we will do for the rest of this course at least, it's dichotomous dependent variable, so that there's only two possible values. Either something did happen or it did not happen. So either people voted or did not vote, either countries are at war or they are not at war, either trade unions go on strike or they do not go on strike. So any kind of dichotomous outcome where something either happens or it doesn't happen. Well, if that's our dependent variable, then what are we doing when we are trying to estimate the effects of independent variables, of x's on that dependent variable? Well, then we are interested in getting effects that tell us something about how the predicted probability that something happens that we're interested in changes if our x variable changes, right? Because, if you look at dichotomous categorical variables, then what we're really interested in is, what is the probability that something happens? So if you want to say, what is the effect of x on the probability of something happening, then we are talking about, what is the effect of x on the predicted probability? Because again, our regression models will give us some kind of predicted value. So that's what we are after. Now there's a couple of things that we already know from last week. So for instance, we know that if we are talking about independent variables, about x variables, then we can just use them in a normal regression model like we always do. The only thing we then need to do is recode them into a dummy coding. So give the value 0 to all the cases that do not belong to some category, and the value 1 to all the cases that do belong to that category. So we saw that we can do this for x variables in a regression analysis, and then we just get dummy coding. we also already saw that we could in theory apply the same trick to our dependent variable, our y variable. So if we take our y variable and code it in such a way that all the cases that did not experience the event that we're interested in get the value 0, and all the cases that did experience that event get the value 1, then we could do that. And we even know by now that if we would then calculate the average of that y variable, that's the same thing as calculating the proportion of observations in which the event took place, which is the same thing as the probability that the event took place. So y bar, the average on our 0, 1 coded y variable, would be the same thing as the probability that y equals 1. So taking the average of a 0, 1 coded variable is the same as calculating probability that the event that you coded 1 will happen. Yeah, so we already know these things from the past lectures. So you might think, okay, so I want to say something about the effects of my independent variables, of my x variables on my dependent variable, and I want to do that in such a way that I get predicted probabilities. Then why not just dummy code my dependent variable, which we know if we dummy code the dependent variable, that will give us, then the mean value of that variable will be identical to the probability. Well, why not just use that dummy coded dependent variable directly in the linear regression model? Because we hopefully remember that, well, regression models are basically nothing more than mean values of our dependent variable conditional on the values of our independent variables. Yeah, so if we take out all the independent variables, then we are left with the unconditional mean, or just the mean value of our dependent variable. If we put in independent variables into our model, then basically our model describes how the mean value of our dependent variable changes if our x variables change. So you might say, well, why not just use a dummy coded dependent variable in a linear regression model? Because then obviously this is going to give us predicted probabilities. So it tells us, well, how does the predicted probability of our of our event happening changes if our x variables go up by 1 unit on their scales? And as a matter of fact, you could do this, and there's actually some sense to that. So sometimes these types of models are used for dichotomous dependent variables. Then they are sometimes referred to as linear probability models. So nothing is stopping you, and it's not even always strictly a terrible idea, but often it is. And the reason it's often not a good idea to do that is because even though at a conceptual level we get a model for the predicted probability, it is quite likely that the estimates that we get are going to be biased if we just use this linear model for a dummy-coded dependent variable. So let's think about, okay, why is that so? Why would our effects, our estimates be biased if we just do a linear regression model with a categorical dependent variable? Well, as always, where does bias come from? It comes from a difference between what we assume to be true and what is actually true about the distribution of our error term. So in other words, we are talking here about the 4 standard assumptions that we already saw that we make when we have a linear or less estimated regression model: the assumption of additivity and linearity, the assumption of independent errors, the assumption of homoscedasticity, and the assumption of normally distributed errors. Yeah, we know that we can summarize all of these 4 assumptions into this one single little formula, that the assumption is that our error term is distributed normally with a mean of 0 and a single variance of sigma square. But that's basically just a formula for these 4 assumptions: so additivity and linearity, independent errors, homoscedasticity, and normally distributed errors, which combined basically just means that, well, if we are fitting a regression line through the observations that we have with the OLS method, so we fit a linear regression line, then it needs to make sense that we are fitting a linear regression line. So that's the assumption of linearity, and if there's multiple independent variables, then it also needs to make sense that we can just add up the effect of each variable to get the predicted value. So that's additivity and linearity. We assume that the distribution of errors around our regression prediction is always more or less the same. So that's the assumption of homoscedasticity. And we assume that this overall distribution of errors is normal. So basically we can think of our regression line as going right over the top of a normal distribution of errors. And it's also the idea that we should not be able to systematically predict the errors of the cases by knowing the values of the errors of the other cases. So in other words, the errors also need to be independent from each other. Yeah, so those are the 4 standard assumptions that we need to make about the distribution of our error term. If there's a problem with these assumptions, if they are not true, if they are violated, as this is often referred to, then we will get some type of bias, either in our regression coefficients or in our standard errors, or in both. Okay, so this is what we already know. Well, if you have a categorical dependent variable, then 3 of those 4 assumptions are going to be problematic. So additivity and linearity is probably not going to be true. Homoscedasticity is probably not going to be true. And normally distributed errors is probably also not going to be true. So of the 4 standard assumptions that we need to make to get unbiased estimates, 3 of them are probably going to be violated, are going to be problematic if you have a categorical dependent variable. So let's look into why that is the case. So let's assume we have a very simple example. So we have just one independent x variable. Let's say it's income, and we have one dependent variable where something either happened or it did not happen for the different cases. So let's say that this is whether or not people voted in an election. And so we might want to analyze, okay, so what is the effect of income on the probability that people vote in an election? So all the people that did vote in the election, they would get the value 1. So for those, the event of voting occurred. And all the people that did not vote in the election, for them, the event did not occur. So we can assume that they get the value 0. And of course, those are the only 2 values that the cases in our sample can score, because there are only 2 different possible states. Either the event occurred or it did not occur. So if there is some kind of, let's say, positive relationship between X in income and whether or not people voted, then what we would see is that we have lots of cases that score the value 0, that have relatively low income, and the further we increase income, at some point we will see that there tend to be more cases that score the value 1, so that did in fact vote. But again, because it's a dichotomous dependent variable, there are only 2 values possible. Either the event occurred or it did not occur, right? So that's a hypothetical situation. Okay, so what does our y-axis represent? Well, it represents for each specific case whether or not they voted, whether the event occurred. But if we look at over our entire sample, then this is basically a scale for the probability of voting. Yeah, because what is the probability of voting? Well, it's the number of events divided by the number of observations. So you could say overall, we could say our y-axis here is also the scale for the probability of voting, right? So we want our effect of income on voting to represent some kind of predicted probability. So, okay, great. So we have these observations. Now let's assume, okay, let's just estimate a linear regression model, because our y-scale, our y-axis is the predicted probability of voting. And then given that in this case we have a positive relationship, our regression line would be something like this, right? We get some kind of positive regression line where we see that with every 1 unit increase in income, let's assume income is measured in deciles of household income. So for every 1 decile increase in household income, the predicted probability of voting increases by some value, which is our B1 coefficient, which is always the same. So it's always the same increase because it's a linear model. So no matter whether we're talking about the step from income decile 1 to 2 or 9 to 10, it's always the same increase in the predicted probability of voting. So we have a linear model for the predicted probability of some event occurring. Now, if you look at this, it looks weird, right? I mean, there's something awkward about this picture. For one thing, we know that we can only observe whether or not the event occurred. And if we think of our model as representing the underlying probability that something happens, we also know that probabilities can't be larger than 1 and they can't be smaller than 0, right? Because again, something can't happen more often than always. So probability can't have a value of more than 1. And it also cannot have a negative value because something cannot happen less often than never. So that's problematic because now we have a linear model that just completely disregards the fact that probabilities can't go over 1 or can't go over below 0, and just draws a straight line that doesn't stop at 1 and it doesn't stop at 0. Because it's a linear model where we always say, well, we have one slope coefficient that represents the effect, so that's always the same effect on the predicted probability. So what's happening here? Well, if we want to correctly model the relationship between income and voting, or in general any kind of x variable and a y variable that's the dichotomous y variable, then we cannot have a linear effect because the effect can't be linear. As a matter of fact, the effect has to somehow flatten out. The further we go towards 1, it has to come down, so it can never go over 1. And also reversely, it has to also flatten out the closer we get to 0, so that we never get predicted values that are below 0. So whatever the effect of x and y is, it has to take somehow a kind of S shape, where we make sure that our predicted values don't ever go below 0 and don't ever go above 1, because those are nonsensical values. So in other words, a linear effect would not be a good representation of the true effect that we can observe, because it can't be a linear effect. Whatever the effect is, we need to make sure that that the effect flattens out if we go towards 1, and that it flattens out if we are going towards 0. So linearity is not a good representation of the effect. And also notice that, if we just fit a linear model, then we might get predicted values that are larger than 1 or smaller than 0, that are negative numbers. And again, for the same reason, that makes no sense, because we are talking about predicted probabilities, and predicted probabilities are just probabilities. So it shouldn't be possible to have a probability that is negative or a probability that is larger than 1, because those values make no sense if we talk about probabilities. So that's an issue that we have here, and this is basically the issue, that we cannot assume a linear effect, because these cannot be linear effects by definition, because we are talking about predicted probabilities. So in other words, our assumption of linearity clearly is going to be violated if we have a dichotomous dependent variable and we fit a linear regression model to that. There's also 2 other problems. Well, let's take a look, and I just extended the range of our regression prediction a little bit here to make the picture clearer. Let's look at, well, what would the distribution of our errors be in this model? Remember, what is the error? It is the difference between what we predict and what we observe for each case. So if we now look at, well, how would the errors be distributed if we just fit a linear regression model with a dichotomous dependent variable? So in this case, we start in the lower left part of the graph. We see that, okay, so we have all these observations that score very low on our x variable, and for which the event did not occur. And so they get these error values, right? So the red lines indicating the difference between predicted and observed. So we already see here that the further we increase 1, the smaller the value of the error is. And then if we go further to the following cases, we see that, but then at some point, once the predicted values are below our regression prediction, then the errors increase the further we increase the value of our x variable. And we see now also that at some point we get these cases where the event did in fact occur. And for those cases we see that, well, the further we increase the value on our x-axis, on our x variable, the smaller the error term becomes. And then at some point the model starts predicting values that are over 1. And then again, we're going to see that the error is going to increase again. So there's something super weird going on with the error distribution in this case, because it is absolutely not the same wherever we look at the x-axis. As a matter of fact, you can quite clearly see that how big the differences are between what you predict and what you observe. So how much variation we have in our error term absolutely depends on what the value of our x variable is. So in other words, our errors would be super heteroscedastic. So there's absolutely no nice homoscedastic distribution of our error term, which is always the same, more or less, no matter where we are on the x-axis. No, this is really quite a bit of heteroscedasticity that we have going on here. And by implication, it's also going to be the case that if we look at the overall distribution of all these values for our error term, this is absolutely not going to be a nice normal distribution where the larger the value of the error is, the smaller the number of observations we have with that error. So this bell-shaped distribution. Okay, so here we also see that if we just do a linear regression model for a dichotomous dependent variable, then we get an error term that would be heteroscedastic, not as assumed under that model homoscedastic, and that's also not going to be normally distributed, which we also assume with a linear regression model. So in other words, also our assumptions of homoscedasticity and normally distributed errors are going to be not true, are going to be violated if we have a dichotomous categorical dependent variable. So in other words, linear regression models for categorical wise, is it possible? Yes, but there's probably going to be a bit of bias and maybe even quite severe bias going on because the assumptions of additivity and linearity, homoscedasticity and normally distributed errors are probably going to be poor representations of the true representation of the true distribution of our error term. So those would be violated. So as always in statistics, we have many different problems, and often we also have solutions to these problems. And in this case, we have a solution, and a solution, at least one of the solutions that we can employ, is the so-called logistic regression model. So logistic regression is basically a way of trying to solve these problems and still being able to do regression analysis. So how does it work? Well, the basic idea is very simple. Instead of taking our original dependent variable as the dependent variable, we are going to transform our dependent variable. And it's basically a double transformation. We are first going to transform our dependent variable from a probability into an odds, so turn p into p divided by 1 minus p, and then take the natural logarithm of those odds. And that's going to be the dependent variable in our model, right? So instead of just having y as our dependent variable, we are going to take the log odds that y equals 1, so the log odds that the event that we're interested in takes place, and use that as a dependent variable. Now, there are different ways to write this model, as I will also show you in this lecture and the next one. And the one that you see in the book that you're reading is the same model the first time you see it, but written in a different way. There's nothing wrong with that. I think for didactically it makes more sense to start with this representation rather than the one that's being used in the book by Field. But as you will see during this lecture and the next one, all of these are just different ways of writing the same model. So I like to think of this as a model where we're transforming the dependent variable from just the probability of the event happening into the log odds of the event happening. So basically doing this double mathematical transformation from a probability into an odds, and then from an odds into a log odds, and take that as the dependent variable of our model. And everything else more or less stays the same. So we still have a b0 coefficient, so the constant value, plus a b1 x1 part, so that's the regression coefficient for the first independent variable, plus b2 x2, the regression coefficient for the second independent variable multiplied by the second independent variable, and so on and so forth. So we basically still have a largely same model as we have had all throughout this course, where we have a constant value and different regression coefficients for different x variables that are included in the model. Yeah, so notice here that I'm just writing the natural logarithm of p divided by 1 minus p, where I'm shortening what I formally should be writing is, what probability are we specifically talking about? Well, formally it's the probability that the event happens, so the probability that y equals 1. So I'm just going to assume, unless we state otherwise, that it's always going to be, if we talk about the probability, then we talk about the probability of the event happening, so the probability that y equals 1, just to keep it a bit readable with these formulas. Yeah. So this is basically this double transformation. So the turning probabilities into odds and then turning those odds into log odds, so taking the natural logarithm of the odds. And this transformation is also often known as the so-called logit transformation. So taking the logit of our outcome variable, of our x variable. So we already saw that there are a couple of different ways of writing log odds. That's what I started out with in this video lecture. So we can write log odds, we can write log e odds, or we can write log ln odds, or log e p divided by 1 minus p, or ln p divided by 1 minus p. All of these things mean exactly the same thing. Well, now we can add one more way of writing that, which is also often used. This is the just writing, well, we take the logit of the probability that something happens. Yeah, so all of these different ways of writing this all mean exactly the same thing, namely that we're going to do this double transformation of transforming p into odds and taking the natural logarithm of those odds. So this is often referred to as the logit transformation, which is also the reason why logistic regression models are sometimes referred to as logit model, and specifically in a situation where it's a binary dependent variable where we observe for each case whether or not some event took place, then it's sometimes referred to as the binary logit model. As always, I'm not telling you these things to confuse you, but because it's going to be useful for you in the remainder of your of your studies, and maybe also the remainder of your life, that you realize that all of these different notations are just different conventions on how to talk about exactly the same thing, because they're going to be used interchangeably quite a lot in practice. Yeah, so logistic regression or logit or a logit model all refers to the same thing, that we're going to transform from p into the logit of p, so the log odds. So we're going to take the log odds of our dependent variable. So if we take a look at this model, so the natural logarithm of p divided by 1 minus p, so the log odds of our dependent variable. Well, what can we already tell from just looking at this model? Well, the coefficients in this logit model give us a linear effect of our x variables on the predicted log odds, that our y variable takes the value 1. So in other words, the log odds that the event that we are interested in happens. Yeah, so our regression coefficients can be interpreted, well, okay, this is how the predicted log odds that the event happens changes with a 1 unit increase of this x variable on whatever scale it is measured at, because, well, we just transformed our dependent variable from a probability into a log odds. And other than that, it's still a model where we have one equal sign and no weird things happening after that. So it's still a linear model, but it's not a linear model for the probability. No, it's a linear model for the log odds that some event happens. So if we have a linear model for the log odds that something happens, then the regression coefficients tell us, well, okay, this is by how much the predicted log odds change with a 1 unit increase in this specific x variable on its scale. So first, well, why would you want to use this logit transformation? Why would you use this logistic regression model? Well, let's consider what this mathematical transformation of turning p into log odds, what it does. Well, it translates the relationship between our x's and the probability that the event that we're interested in happens, actually happens, into an S-shaped relationship, which is the appropriate relationship. Well, why does it work like that? Well, check back the pictures I showed you in the B lecture last week, and also the corresponding Excel sheet on Brightspace, and you will see, well, because that's the mathematical relationship between log odds and p. So if we transform a variable from a probability into a log odds, then if we take a look at, well, okay, how are these log odds then related to the probability that we started out with, then we will see that there is an S-curved relationship between the two, that if the log odds go up linearly, then the corresponding probabilities will increase following this S-shaped relationship. So this fixes the problem that we can't assume linear relationships by changing the relationship with the predicted probability from a linear relationship to an S-curved relationship. Yeah, so logistic regression models are linear models for the log odds, Yeah, so not for the probability, but for the log odds. But because the log odds have this S-shaped relationship with the probability on which they are based, that means that we get this S-curved relationship for predicted probabilities. So in other words, this problem mathematically solves the problem that we can't assume a linear relationship, that we should actually assume that there is some kind of S-shaped relationship by specifically making sure that that is actually the case. That we actually get a model for probabilities that is not linear, that follows this S-shaped. And there is a second thing that this model does, namely it makes an assumption about how our events, the number of events that we observe, so correspondingly the probability that our event happens, how that is distributed. Specifically, it assumes that the number of events follows a so-called binomial distribution. Now, what is a binomial distribution? It's basically a distribution that we could use if we wanted to describe the behavior of a coin flip. Yeah, so taking a coin and flipping it to see whether it comes out heads or tails. If we would look at, well, how often do heads and tails happen? If we do that many times over, that's the so-called binomial distribution, which makes sense because we are looking at how we can explain whether or not some events take place, and that's basically the same logic. Something either happens or it does not happen, and it's the same logic as, well, flipping a coin. Yeah, either it comes out heads or it does not come out heads and therefore comes out tail. Yeah, so that makes a lot of sense to assume a binomial distribution of our dependent variable, of the number of events that we observe. But that also means that the binomial distribution also tells us something about, well, okay, how is then the error distributed? Because it also applies a specific distribution for our error term, because that's the logical consequence of assuming a binomial distribution for the observed number of events. So in other words, with these models, we assume that the distribution of our error term is consistent with the binomial distribution. Which also means that what we are not assuming in that case is that the errors are homoscedastic or normally distributed. We're actually assuming a different type of distribution of errors, where for one thing, we assume that how large the error is actually itself depends on what the value of our x variables are. So it is already intrinsically a heteroscedastic distribution of errors, which is also the reason why there is no error term added to this model. That's not because we assume that our model all of a sudden has become deterministic and is perfectly able to predict the outcome. No, we still assume that there is an error, but there is no longer an error that we can just independently add to our regression equation that's always the same, because now the value of the error actually depends on what the value of our x variables are. So it's an assumed distribution of the error term. Now, exactly what the distribution of the error term looks like and why that makes sense for logit models is something I'm going to come back to in the B lecture. So for now, you don't need to worry about it too much yet, but just know that basically what we are doing with this logistic regression model is, by taking this mathematical transformation from P into log odds, we are fixing the problem that we can't assume linear effects. And secondly, by assuming a binomial distribution, we are fixing the problem that we also cannot assume that our errors are homoscedastic and normally distributed, because we are now allowing the errors to follow another type of distribution. So that's basically the logic behind the logistic regression model, that by doing this, we're basically fixing the problems that we would have with the linear regression model, so we still can get unbiased estimates. So let's look at a specific example that's very simple. Let's say that we have one x variable. Let's again stick to the example that we are interested in analyzing the effect of income on voting, and we observed whether or not people voted, and we observed their income, and we're fitting this logistic regression model, so taking the log odds of voting as a dependent variable, and then estimating a b0, a constant value, and a b1 coefficient for the income effect for the x1 variable. Then if we would assume it's going to be some kind of positive effect, then if we would calculate through what that effect means for predicted probabilities of voting, then it would give us this S-shaped effect on the predicted probability on voting. Again, the model is a linear model for the log odds. So our B1 coefficient itself would tell us about what is the linear effect of income on the log odds of voting. But if we would then use that to calculate, okay, so what would be the corresponding probability, then we would see that this gives us this S-shaped effect on the probability of voting. Yeah, so in an abstract sense, that is what's going on with this logit transformation. It transforms our dependent variable in such a way that we get predicted probabilities from our model that follow an S-curve if it's a positive effect. If it would have been a negative effect, which of course also could happen, then you can think of that as following this kind of reverse S shape, this S where we basically it would be something like starting here and then going down and flattening out here, so a reverse S-shaped. So that's at an abstract level how you can think about these effects in logit models. So a positive effect implies an S-shaped effect of X and Y, and a negative effect implies a reverse S-shaped effect of X on Y. And of course, we could extend that with more than one X variable. So for instance, we could include potential confounding variables as control variables or other variables that we have hypotheses about and include them in our model. So we can still have a multiple regression model, just not a multiple linear regression model, but rather a multiple logistic regression model, which of course is going to be super useful if, for instance, we want to make better causal inferences. So in general, remember, we discussed this already, but there is a monotonic relationship between any kind of variable and the natural logarithmic transformation of that variable, which means that higher predicted log odds also imply higher odds, because there is a monotonic relationship between some variable and its natural logarithm. That means there's going to be a monotonic relationship between the odds and the natural logarithm of those odds. In other words, there is a monotonic relationship between odds and log odds. And there is also a monotonic relationship between odds and p, which we also saw already as well, which means that higher predicted log odds imply higher predicted odds, and also higher predicted odds imply higher predicted probabilities. Again, because there is a monotonic relationship between the probability and the odds. So if the odds goes up, then the probability goes up, just not at a linear in a linear fashion. And there is a monotonic relationship between the odds and the natural logarithm of the odds, but again, not a linear relationship. Yeah, so overall we could say, well, higher predicted log odds imply that the predicted odds would also increase, and higher odds also imply that the predicted probability would increase. So in other words, how can we now in general interpret these regression coefficients in a logit model other than just saying, well, this is by how much the predicted log odds increase? Well, if you have a positive coefficient, that means that the predicted log odds increase, but that also means that by implication the predicted odds increase, and also that the predicted probability that the event that we're interested in increases. Again, because there is a monotonic relationship between all three of those numbers. Not a linear relationship, but yes, a monotonic relationship. If one goes up, the other also goes up. And it also means that negative coefficients in general imply that the predicted log odds decrease, but that also means that the predicted odds will decrease, and that the predicted probability that the event occurs decreases, again because there is a monotonic relationship between these three values. So at an abstract level, this is how we can interpret these regression coefficients in a logistic model. Now, it's of course nice to have estimated regression coefficients in a sample, but we want to also probably say something about some underlying population, or in general some underlying unobservable data generating process. How can we do that? Well, test for statistical significance, and that we can basically do in the same way that we always did, by formulating some null hypothesis about an assumed value of our regression coefficients in a population, and test, well, how likely is it that we find in our sample what we find if that null hypothesis is true, and is that so unlikely that we maybe can reject that null hypothesis. So as always, a sensible null hypothesis, if we're talking about coefficients in a regression model, is, well, assume that there is no effect in the population. So in other words, use the null hypothesis that your regression coefficient b takes the value 0 in the population, and then we can test that null hypothesis against, for instance, the alternative hypothesis that it is not zero, or that it is positive, or that it is negative. Yeah, so that logic stays exactly the same. The only thing that changes is the test that we use to evaluate that null hypothesis. So if you do a logistic regression model in SPSS, it's not going to give you a t-value because that's not really appropriate for these models. Instead, it's going to present you the so-called Wald test, named after Abraham Wald, who basically did the mathematical groundwork for this test, which is, again, based on looking at what is our estimated regression coefficient and our standard error, but in that case, we take the regression coefficient divided by the standard error and square the result of that. So instead of just b divided by SE, we are getting b divided by SE squared, and we're going to assume that that follows a chi-squared distribution. So this little x here that looks like an x is not really an x, it's the Greek letter chi, and the 2 of course stands for chi-squared. So we're going to assume that this ratio of coefficient divided by standard error squared follows a chi-squared distribution where the degrees of freedom are always going to be 1. So we can look at, well, okay, what is coefficient divided by standard error squared? What's the value of that? Compare that to the chi-squared distribution with 1 degree of freedom to see, well, how far out in the tail of the distribution is this chi-squared value, this test statistic, to see, well, what is the associated probability value, p-value, with that, and is that so small that we are confident in being able to reject our null hypothesis. Yeah, so that's it's quite similar to using a t-test. It's just that we're using a different test statistic and a different theoretical sampling distribution, the chi-squared distribution in this case, because that's more appropriate for logistic regression models. And as always, of course, you don't ever need to do this manually because SPSS does it for you, but you should understand what the underlying logic is of where does that p-value that SPSS gives you, what is it based on, where does it actually come from. Yeah. So as always, I mean, the logic stays the same. If your probability value is smaller than your chosen level of significance, so your alpha level, you can reject your null hypothesis and say, well, there is a statistically significant effect. As always, of course, yeah, remember there is nothing magical about setting alpha to 0.05. This is really just a tool you can use to make a meaningful decision, but you still as a researcher have to make a meaningful decision, of course, taking into account your desired alpha level, but also, well, how large is my sample, how large is the assumed effect size in the population, so how much statistical power do I have? But the basic logic is exactly the same as with t-tests in the linear regression model. So all of that was the abstract introduction, which is probably going to be a bit, has probably been a bit dizzying. So let's look into a concrete example. So let's say I want to analyze the probability of voting in, let's say, a national election, and I measured this for different people in a sample of people. So I know whether or not they voted in the last national election, and I know, okay, whether or not they voted, that's a dichotomous dependent variable. So I'm probably going to need some kind of logistic regression model, and I want to use a logistic regression model to estimate the effects of gender, age, and income. Yeah, maybe I have a hypothesis about these effects, or some of them, and maybe other of them are control variables. So let's assume this is the logistic regression model that I'm going to estimate. So the natural logarithm of the odds of voting, so in other words, the log odds of voting equals B0 plus B1, a female dummy variable in this case, plus B2, an age variable measured in years, plus B3, income measured in household income deciles, and actually did this using the European Social Survey data from 1 or 2 waves ago. And then SPSS is going to give you a whole lot of output if you do a logistic regression model. So this is just the last table that SPSS gives you that we are looking at here, because that's the one where the actual regression coefficients are reported. So just taking a look at that very last table, this is the results that I got from estimating this model. Yeah, so as always, we can just start writing down what our estimated model is. So we start out with, well, what is our dependent variable? Our dependent variable are the log odds of voting. So the natural logarithm of the probability that people voted divided by 1 minus the probability that people voted. And then we can just fill in the formula. Well, starting with, well, what is the value for B0? Now, very confusingly, SPSS reports the value for B0 for our constant value at the bottom of the table if you do a logistic regression model, whereas in the linear model we saw that it's at the top of the table. There is no reason for that other than that, well, it's at some point there were just different programs for logistic and linear regression model, and they used different conventions, and later on they were merged into the same SPSS architecture, and now we are stuck with this confusing situation where the constant is at the bottom in logistic regression models and at the top in linear regression models. So once you know this, you don't have to worry about anymore as long as you know where to find the constant. So in this case, the estimated regression coefficient for the constant was estimated to be minus 0.873. So we can fill that in the formula. And then we can look, well, okay, what was the regression coefficient for the female dummy? Well, that was estimated to be 0.099. So now we can fill in that, and we see that we have an estimated regression coefficient for age of 0.025. So we can fill in that in the formula, and we have an estimated regression coefficient of 0.177 for income. Right, so okay, now we have already taken our SPSS output and just used that to write out our logistic regression model. And for now, and also for the assignment, all you need to worry about is the last table that SPSS spits out where these regression coefficients are reported. All the other tables are going to be things that I talk about in the B lecture, which you can also watch after you worked on the assignment. Okay, but this is the really important part, the regression coefficients themselves, so the actual model that we're estimating in the last table. So this is what the estimated model looks like. So now we know the values for B0, B1, B2, and B3. Now let's look at, okay, how do we now interpret them? Well, we know that our model is a linear model for the predicted log odds. So we can just start interpreting our regression coefficients, and then let's start with, okay, what does the p-value tell us? Well, for the female dummy variable, we see a quite high p-value of 0.443. So it's quite likely to find this regression coefficient of 0.99 for female with this standard error of 0.12. If there is in fact no effect of differences between men and women in voting, controlling for differences in age and income. So in this case, we could say, well, controlling for the effects of age and income, there is no significant difference between men and women in the predicted log odds of voting. We do, however, see that there is a fairly low p-value for the age effect. So let's interpret the coefficient for the age effect. Well, the coefficient that we found was 0.025. Well, what does that mean? Well, it means that controlling for the effects of gender and income, the predicted log odds of voting increase by 0.025 points for every year a person is older. Yeah, so for every year a person is older, controlling for the effects of the other variables in our model, the predicted log odds of voting increase by 0.025. And remember, it's a linear model for the log odds, so we can just interpret these regression coefficients as coefficients that tell us about the change in the predicted log odds. And it's a linear change, so it's always the same change. And we can also do the same for the income effect. So we find a quite low p-value, and we see that the estimated regression coefficient is 0.177. So how do we interpret this? Well, controlling for the effects of gender and age, the other two variables in the model, the predicted log odds of voting increase by 0.117 for every 1 decile increase in household income. Yeah, so we can now directly interpret these regression coefficients as, okay, this is how the predicted log odds change with a 1 unit increase on our x variables on whatever scale they are measured at. So that's great, it's correct. The only problem with this is it is not very intuitive, because now we are talking about, okay, how do the predicted log odds of voting change when income or age changes? But yeah, log odds, that's based on a double mathematical transformation, first from probabilities into odds, and then from odds into natural logarithm of the odds. So that's difficult interpretation, especially if you would be talking to people that are maybe not as mathematically gifted as you are, undoubtedly are, then explaining, well, exactly what does that mean, how big is the effect actually, is going to be quite a task, right? Because it's on this weird log odds scale. So the question is, can we make this a bit more intuitive than interpreting these effects as changes in the log odds? And the good news is, yes, that we can actually make it a bit more intuitive, because mathematically we can also rewrite this model in a different way. Specifically, we can get rid of the natural logarithm that's now on this side of the equation and put it on that side of the equation. So we can get rid of the natural logarithm, meaning that we can just talk about the predicted odds rather than the predicted log odds of voting. So we're already getting then rid of one of these two mathematical transformations that we used. So we can just rewrite the model in such a way that we put the natural logarithm on the right hand side, which mathematically means that that's equivalent to transforming it into this model, where we take the value for E, Euler's number, remember that number that's around about 2.718, to the power of the first coefficient, multiplied to Euler's number E to the power of the second coefficient, multiplied by the value of our x variable, multiplied by the value of the third coefficient, multiplied by E to the power of the second coefficient, multiplied by the x2 value, and so on and so forth. So in other words, what we have here is we have a multiplicative model, because instead of adding things up, we are actually multiplying things to get a predicted value. In this case, the predicted value are the odds. And what we do is we exponentiate our regression coefficients, and then this tells us by how much we can multiply our predicted odds if our x variable goes up by 1 unit on its scale. So we have an additive linear model for the log odds, which we can rewrite as a multiplicative model for the predicted odds. So here we see a type of model that is not additive. Remember the assumption of linearity and additivity. In this case, it's not an additive model, but a multiplicative model where we have to multiply things. So, which means that we can now just look at our regression coefficients that we estimated and exponentiate those, and those will tell us by how much we can multiply the predicted odds. In other words, our regression coefficients, if we exponentiate them from the original logit model, can be interpreted as odds ratios. Remember what is an odds ratio? It tells us by how many times we can multiply the odds of something happening by a 1 unit increase in some x variable. So now we see that we can actually rewrite the model, our logistic model, in such a way that we can interpret our effects as odds ratios. So again, taking the same table, I just rewrote the model in such a way that now I've gotten rid of the natural logarithm here and put it over here by using this mathematical trick. So now I have p voted divided by 1 minus p vote. In other words, now I have a model for the predicted odds of voting rather than the log odds of voting, and that works out to Euler's number to minus 0.873, the constant value, multiplied by Euler's number to the power of minus 0.99 times female, so the regression coefficient for the female dummy, multiplied by Euler's number to the power of 0.255, multiplied by the value of h, so that's the coefficient for h that we found, multiplied by Euler's number to the power of 177 times income for the income coefficient that we originally found. Which of course you could do manually, and you definitely should try to do manually for yourself, so you actually know how it works. But SPSS is nice enough to always do this automatically for you. So the last column in this table, where the heading is exp, xp stands for the exponentiated version of our original b coefficient. So you can. You could just do this manually with your calculator, but SPSS does it for you, so check to make sure that it's actually correct. So Euler's number to the power of minus 0.873, the original coefficient that we had, works out to 0.418. Euler's number to the power of 0.099, the original coefficient that we had for the female dummy, works out to 1.104. Euler's number to the coefficient that we found for H, 0.025, works out to 1.025, and Euler's number to the power of 0.177, the coefficient that we found for income, works out to 1.194. So that's quite nice of SPSS. We actually don't need to do this manually. It already does this for us. So now we see that in our regression table, we have the original coefficients that tell us about what is the effect of our independent variable on the predicted log odds. So that's under the heading B. But we also see, okay, what is then the effect if we express it as an effect on the predicted odds, which is under the heading XB, the exponentiated version of our B coefficient. And notice that we could go back from our exponentiated version of the coefficient that we have here, from this value to the value of the original logit coefficient, simply by taking the natural logarithm of that coefficient. So the natural logarithm of 1.104 works out exactly to this 0.099 coefficient that we started out with, the natural logarithm of 1.025, so the odds ratio effect of H, taking the natural logarithm of that works out to the original logit coefficient that we had of 0.025, and the same thing for our income variable, the odds ratio coefficient of 1.194. If we take the natural logarithm of that, we are back at the original value of 0.177. And of course, the same is also true of the constant. So the odds ratio of 0.418. If you take the natural logarithm of that value, you are back at minus 0.873. Yeah, so notice here that we can have positive and negative coefficients if you're expressing the effect as an effect on predicted log odds. Yeah, so here, for instance, we have a negative coefficient for the constant, and in this case, all the other ones happen to be positive because they are all positive effects of female age and gender. But in principle, we could have both positive and negative effects, and so then the logit coefficients are either positive or negative, indicating whether or not there is a positive or negative effect on the predicted log odds. If you then look at, well, what are then the corresponding values if you take the odds ratios, so the exponentiated version of those coefficients, well, then it's always going to be a positive number, but it's either going to be a positive number that's larger than 1 or smaller than 1. So if we have a positive effect, then we get an odds ratio coefficient that's larger than 1. If we have a negative effect, we get an odds ratio coefficient that's smaller than 1. Yeah, remember when we first talked about how to interpret odds ratios, that seems to make sense, right? So positive effect means odds ratio larger than 1, negative effect means odds ratio smaller than 1. And of course odds ratios mathematically can't ever be a negative number. Yeah, so it's either between 0 and 1 for a negative effect, and from 1 to infinity for a positive effect. Okay, so let's look at how to specifically interpret these odds ratio coefficients. Well, they are literally the multiplier of the odds. So it's a multiplicative model for the predicted odds. So these exponentiated coefficients tell us by how many times can we multiply the predicted odds, in this case of voting, of the event that we are interested in, of that event actually occurring. So for instance, this odds ratio coefficient of 1.025 that we found here for the age effect. Well, how can we interpret that? Well, controlling for the effects of gender and income, the predicted odds of voting increase 1.025 times for every year a person is older. Yeah, so for every year a person is older, we can multiply the odds, the predicted odds of voting by 1.025 times. Yeah, by 1.025. So it's a multiplicative model. So it's not, this is by how much the predicted odds increase, but by how many times the predicted odds increase. Yeah, so by how many times we can multiply the predicted odds. 1.025 in this case. Which with a trick we can also make even a little bit more intuitively understanding, because we can also express this as a percentage change. And we can do that by simply taking the value that we find for this exponentiated coefficient, for this odds ratio coefficient, minus 1, and multiply that by 100. So basically, what is the difference between the coefficient and 1, and then whatever that difference is, multiply that by 100 to get a interpretation as a percentage change. So in this case, we see that the odds ratio coefficient for the H effect was 1.025. Well, 1.025 minus 1 times 100 works out to 2.5, which means that we can also interpret this effect as indicating that the predicted odds of voting increase by 2.5% for every year a person is older. Both of these are correct and equivalent interpretations, but the second one is maybe a little bit easier to understand than the first one. Yeah, so both of those can be used. So we can also do the interpretation for the income effect. So we had an odds ratio coefficient of 1.194. How do we interpret this? Well, it's a multiplicative model for the predicted odds. So it tells us, well, controlling for the effects of gender and age, the predicted odds of voting increase by 1.194 times for every 1 decile increase in household income. Yeah, remember, it's a multiplicative model for the predicted odds. So it tells us by how much can we multiply the predicted odds for every 1 unit increase of income on its scale, which in this case happens to be deciles. But again, we can use the same trick to express this as percentage change. So 1.194 minus 1 times 100. So the difference between the coefficient and 1 and that multiplied by 100 works out to 19.4, which means that we can also equivalently interpret this effect as saying, well, controlling for the effects of gender and age, the predicted odds of voting increase by 19.4% for every 1 decile increase in income. So that's how to interpret logistic regression models for now. So we saw that the logistic regression model is a model for the predicted log odds, so linear model for the predicted log odds. So we can interpret the regression coefficients as effects on the predicted log odds, but we can also transform this into a multiplicative model for the predicted odds, and then interpret the exponentiated coefficients as by how many times the predicted odds are multiplied for every 1 unit increase of our independent variables. So these are all equivalent interpretations. Mathematically, they're all the same, so it doesn't matter so much for that. But of course, a big part of science is not just doing things that are mathematically correct, but also being able to understand what's actually going on and being able to make other people understand what's actually going on. So it's useful that we can simplify the interpretation of these coefficients a bit, which is the reason why this odds ratio interpretation is a bit nicer, a bit more intuitive than the log odds interpretation. Of course, it would be even nicer and even more intuitive if we can just say something about, okay, well, how does the predicted probability actually change with a 1 unit increase in our X variable, which we also can do. But I'm not going to right now, because this is already enough for now to get you started and to get working on the assignment. But in the B lecture, of course, I will show you how to do that, because it's a little bit more labor intensive to do that. Yeah, so that's it for now. Have at least some fun on the assignment, or at least not too much despair on the assignment. And as always, if you need help, you know where to find us. We are always there for you during the Zoom sessions. Bye bye. Ciao, ciao.